Welcome everyone to the session of the Messaging Layer Security Protocol Basics and Fundamentals. I am Divyang and currently working for Cisco Systems. What is MLS? MLS looks new term, but not really. We know WhatsApp is providing end-to-end encryption and so as few other apps as well. Right now, everyone is using proprietary protocol to achieve end-to-end encryption. Like WhatsApp is using Signal protocol and everyone has some or the other limitations. Like in WhatsApp, you can keep limited size of group. So, to overcome these limitations, group of companies and institutes like Cisco, Inaria, Facebook, Google, University of Oxford, and Wire came together to standardize one protocol as IETF draft. And that protocol is called the Messaging Layer Security Protocol, in short MLS. In this session, we will see what are the problems faced to achieve end-to-end encryption and how MLS is solving those problems. In TLS Basics and Fundamentals, we have seen that TLS or SSL have solved two major problems. First, how to exchange key securely. Second, how to manage identity to prevent man-in-the-middle attack. Both of these problems are equally applicable to MLS as well. In this session, we will consider only key exchange part and see what are the difficulties we will face when we will try to solve key exchange issue using TLS and why do we need separate protocol called MLS. Throughout this entire session, please keep in mind that MLS also need identity management separately, but we will concentrate only on key exchange part. Before starting our session, let's see what is the core of MLS. Asynchronous write chat tree. This is what a typical asynchronous write chat tree look like. Here you can see that A, B, C and D are actual users and all of them have secrets as you can see 5, 13, 3, 17. These secrets are completely private and they are not sharing with anyone. Means A's secret will not be known to B, C or D. Still, the algorithm is designed in a way that each participant enter their secret and derive a same group key. For example, A enters secret 5 and derive group key 15. Same way, B enter secret 13 and derive group key 15. And not necessary that users have to enter keys at the same time. So, this is called typical asynchronous red chat tree and we will see in detail how it is formed and how it will works. But before begin to our session, one question. What is the meaning of red chat? A dictionary meaning? Okay, let me show you one animation. This is called red chat wheel. Can you see a distinguished property of this wheel? This wheel is rotating in one direction only and not allowed to rotate in reverse direction. We will see that how red chat tree will have this property inside. So, let's begin our session. And to begin our session, let's identify problems that is being solved by MLS. What we will do is derive all problem statements together and then see how can we solve them one by one using MLS. To derive problem, let's develop a messaging service. Let's check what do we need to develop a messaging service. One server on cloud and subscribers. So we have Alice and Bob. Now Alice wants to send message to Bob. How she will send message to Bob? She will establish TLS connection with cloud server, and cloud server will establish another TLS connection with Bob. Here you can see that both are using TLS connections, and that is why no one can see conversation between Alice and Bob. But here connection is not end-to-end encrypted. Each message will be decrypted by server and re-encrypted by server, which means server can see all messages sent by Alice and Bob. So here comes our first problem statement: end-to-end encryption. Let's remove two TLS connections. Now we will do end-to-end TLS connection. What does it mean? Here we will modify TLS protocol in such a way that server will have separate TCP connection to each participant, but key exchange happen end to end. Let's see how does this works. Server will relay all key exchange messages between Alice and Bob. Let's see how does they exchange key using end-to-end TLS. Alice send client hello. That will be relayed by server without any modification. Bob send public key. Of course, this key go along with certificate, and that will again relay by server without any modification. And protocol goes on. Using this technique, Alice and Bob can exchange symmetric key securely, and we can achieve end-to-end encryption as well. And they are keep going with this secure connection for a long time, like days or months. Now think, one hacker on internet capturing all packets that has communication of Alice and Bob. Even though all packets are encrypted and hacker cannot be able to decrypt, still hacker has captured those packets. One fine day, hacker hacked Bob's device and steal his private key. You know the importance of private key. Using this key, hacker can decrypt all conversation that he has captured in past. So, this is our second problem statement. If I am doing conversation now, how can I keep my conversation secure in future as well? This is called future secrecy, or more formally called forward secrecy. And keep in mind that because TLS is also facing this issue, TLS 1.3 came up with very strong solution of this problem. We will see what is the solution and how it will protecting forward secrecy. But before looking that, let's move to our next problem statement. For now, we are ignoring forward secrecy issue and considering same solution. Let's say Alice wants to send very first message to Bob and start conversation. So how Alice and Bob exchange key, let's see in detail. Day 1. Alice send client hello to Bob. By the time Bob received this message, Bob goes offline. After 2 days, Bob came online. Day 3. Bob has sent public key to Alice. Now, here if you think that how come after 2 days message reached to Bob and timeout not happen? So, in last problem statement, I have told you that we are modifying TLS protocol in such a way that server has separate TCP connection to each participant and relay the packet end to end. By the time Alice received this key, Alice went offline. After 2 days, Alice came online. Day 5. Alice encrypt key and send it to Bob. Now luckily Bob is online at that time, so key exchange finished fast. Here you can see that just to send very first message to Bob, system took 5 days, even though Alice and Bob both came online multiple times. And of course, this time can vary based on availability of both. So here is our third problem statement: asynchronous handshake. I hope you understood these three problem statements. The difficult part in MLS is understanding problem statement. If you understand problem statement properly, then solution will be very easy for you. We have two more problem statements. Let's check that as well. As of now, we have seen one-to-one communication. Alice wants to communicate to Bob. Now I want to add group management to our messaging service. Alice wants to form a group between Alice, Bob and Charlie. In short, A, B and C. What could be a possible solution? Alice established TLS connection between A and C and derived key called AB. Alice established TLS connection between A and C and derived key called AC. Bob established TLS connection between B and C and derived key called BC. Remember that all connection happen via server. Just to keep diagram simple, we are hiding server. With this method, let's check how broadcast will work. Alice wants to send message to group. She has to encrypt message with key AB and send encrypted message to B. Encrypt message again with key AC and send encrypted message to C. And if group has 200 participants, then Alice has to send same message 200 times, which means Alice cannot take advantage of server to broadcast message. So this is loss of bandwidth and processing power both. That is why we are not proceeding with this solution. What is the next solution? Let's say each participant come up with their own keys. Alice established TLS connection with Bob, and immediately after that Alice provide key A to Bob and Bob provide key B to Alice. Alice established TLS connection with Charlie, and immediately after that Alice and Charlie also exchange their keys. Similarly, Bob and Charlie also exchange keys, not showing here to keep diagram neat. Now, if Alice has to send message to group, then she just encrypt message with key A and send encrypted message to server. Server will broadcast message to all participants in group. When Bob and Charlie receive this message, they will identify that message is coming from Alice and use key A to decrypt it. This is called sender key solution because sender use its own key to encrypt message before send, and receiver will use sender's key to decrypt message. Similar solution is adopted by WhatsApp and Signal. Now, David want to join group. So, David come up with his own sender key called D and exchange his key with everyone. Now, David has key of Alice, Bob and Charlie. Same way, Charlie has key of Alice, Bob and David, which means everyone has key of every other participant of group. After some time, everyone has decided to remove Charlie from group. They have removed Charlie from group. Now any message that will send to group will not reach to Charlie because server has removed his entry from group list. But you know, Charlie has sender key of everyone. which means if he can capture network packet, then he can decrypt all group conversations. So here is our fourth problem statement called post-compromise secrecy. How to solve this issue? One solution is when someone gets removed from group, all users will re-exchange key with others. Consider 201 participants are in group. We are removing one participant from group. So everyone has to exchange key with other 199 participants, which means traffic on server will be 200 multiplied by 199 requests. So here is our final problem statement. Key exchange traffic. And with this, here is all our problem statements that we are going to solve with MLS. First, end-to-end encryption. Second, forward secrecy. Third, asynchronous handshake. Fourth, post-compromise secrecy. Fifth, key exchange traffic for add and remove of members. Hope you have understood all problem statements. Again, I am repeating, understanding of problem statement is the most important to understand MLS. If you understand problem statement properly, then solution will be very easy for you. Let's solve them one by one. We have seen that by taking server as a relay, we can achieve end-to-end encryption. So let's take forward secrecy. Here we are using RSA algorithm to do key exchange. We have already seen this method in TLS basics and fundamentals. Here, if by any chance private key get leaked and hacker has captured all packet from beginning, then entire conversations will get exposed. Do we have any other method to do key exchange? Let's find. Alice and Bob want to exchange key. They will use special match formula to exchange key. All communication here is in plain text and open to everyone till key exchange finish. Alice come up with one simple match formula called x raised to y equal to r. Define value of x equal to 3. Generate random value for y equal to 5. This is the secret of Alice. Using these two values, calculate value of r called RA. Except y, send all other information to Bob. Bob receive this information and generate random value for y equal to 3. This is the secret of Bob. Calculate r called RB. Send it to Alice. After receiving information from Bob, Alice reconsiders same formula. In this formula, Alice replaces value of x with RB and calculate the key. On the other side, Bob also consider same formula. Replace x with RA. Calculate the key. Here you can see that both has kept their y value secret and still derived same key. The essence of the formula is this. I hope you understand this method. Now you must have question here that if we expose value of x and value of r, then it will be easy for anyone to calculate value of y. How to secure private info or secret? Let's understand how reverse engineering works in maths. Let's say I have formula x plus y equal to r. From value of y and r, I want to derive value of x. I can use x equal to r minus y, means plus has reverse operator minus. Same way, multiplication has reverse operator division. X raised to y equal to r. To get value of x, I can use root. Again, x raised to y equal to r. To get value of y, I can use logarithm. So, how can I protect value of y, which is secret of user? There is one operator in maths which has no reverse operation. The operator is modulo. This will return reminder. For example, when you do 5 divided by 2, then reminder is 1. Let's take one formula. X module 5 is 1. What could be the value of x? It could be 1, 6, 11, 16, and gaze will goes to infinite. Means we cannot reverse the result even though we know all values except x. Let's see how can we use this in our formula to protect users' secret. Alice come up with slightly different formula. You can see the change in formula. Alice take x equal to 7, z equal to 23. Generate value of y equal to 12. Alice secret. Calculate RA. Accept y, send all other information to Bob. Now Bob generate y equal to 15. Bob's secret. Calculate RB. Send it to Alice. Alice reconsider formula, replace x with RB and calculate the key. On the other side, Bob also reconsiders same formula, replace x with RA, calculate the key. You can see here how both has protected their secret info and still derive the same key. If someone on network capture all information exchanged between Alice and Bob, then also he cannot derive same key. Of course, in actual, the formula is more complex and values are 2000 bit to 4000 bit long. So it is extremely difficult to brute force. I hope you understand this formula and key exchange method. So, before proceeding to our original problem statement, let's see founder of this formula and method. Whitefield Diffie, Martin Hellman. These two mathematicians has defined this formula in 1976 and later Ralph Markle has made it stronger. Basically, he came up with criteria on how to choose value to make this formula much stronger. And this formula is named as Diffie-Hellman Markle. More formally, we are calling it Diffie-Hellman. And this is the way they have presented formula. So let's come back to our problem statement. Forward secrecy. How can we resolve the problem? Let's use this formula. So we do not need RSA keys and the RSA call flow as well. But we need RSA key for identity management. Anyway, that will be separate things. Let's consider key exchange only. Alice is generating secret y equal to 12. Send formula and all public information to Bob. When Bob receives all information, he is generating secret y equal to 15 and derive common key. Send result to Alice. On receive information from Bob, Alice also derive common key and they have established a secure channel. You can see here that there is no dependency to hold this secret for a long. Each time you can generate new secret, based on that you can exchange new key. So this secret is ephemeral. Ephemeral means short-living and periodically get changed. And hence, if your private key get compromised, then also your communication will remain protected. Now you might have questioned that if ephemeral key will solve the issue, then we can generate private key each time before establishing connection and keep private key short-living. The answer is private key is directly associated with identity and same as public key. And we cannot change identity frequently. That is why RSA keys are long-living keys. I hope you understand as of now. So, before picking up our next problem, let's understand Diffie-Hellman with different use case. Let's understand file vault basics and fundamentals. For that, we will develop file vault. What is file vault? This is my hard disk. This is boot section. This is metadata section. All OS and users login related informations are stored here. This is my file system. This I want to encrypt. So, what is the issue? I will take password from user. Using password, I will encrypt my file system. And password is stored into user's brain. The issue is, if user lost password, then is there any way to decrypt file system? Let's give recovery support to our solution. Let's take password from user. Generate recovery key, a random number. Bring Diffie-Hellman formula. Define constant values. Using this formula, generate public info. Using cross combination means password and public info of recovery key, or recovery key and public info of password. Generate a common key. Use the key to encrypt hard disk. Store public information and constant into metadata section. Password store into user's brain. Recovery key is in locker. This looks good. But what happens if my company enforces me to change password? On change password, my key gets changed and I have to re-encrypt entire hard disk. And re-encryption of entire hard disk will take hours of time. So how do I provide password change support? Let's generate password key, a random number. Generate recovery key, another random number. Bring Diffie-Hellman formula. Define constant values. Using this formula, generate public information. Using cross combination, generate a common key. Use this key to encrypt hard disk. Store public information and constant into metadata section. Now, what to do with password key? Where to store? Let's take password from user. Encrypt password key with password and store encrypted password key into metadata section. User password store into user's brain. Recovery key store into locker. If user has to change password, then need to re-encrypt password key only. That's it. Now our password change is very quick. This method can be improved further, but I am leaving it to you. The conclusion is, using Diffie-Hellman formula, we can solve various security related problems as well. Actual file system or actual file vault may vary and involve various combinations of formulas to achieve strong security. This is about file vault basics with support of recovery key and password change. We have seen two algorithms of asymmetric cryptography. Diffie-Hellman, invented in 1976. RSA, invented in 1978, which we have seen in TLS Basics and Fundamentals session. And to take advantage of both algorithms, there is one more protocol developed called HPKE, hybrid public key encryption. This is what being used in MLS to make it more stronger. To keep our session simple, we are not going deep into HPKE and continue with Diffie-Hellman only throughout this entire session. So let's back to our next problem statement. Asynchronous handshake. Here we have seen that to send very first message, system is taking long time. Even both users came online multiple times. So how do we resolve this issue using Diffie-Hellman? Let's take server. Declare common formula and define constants by server. Let's install CloudDB called key package. We have one user, Alice, who want to sign up with our service. Alice generate random secret, calculate public info and sign up with server. Here you can see public info is stored in DB. We have another user, Bob, generate random secret, calculate public info and sign up with server. Again, public info is stored in DB. Let's see how handshaking happened. Day 1. Bob is offline. Alice asks Bob key package from server. Server return key package of Bob. Using Bob's public info and own secret, Alice derive a key. Using this key, encrypt message and send it to server. Day 5. Bob came online and Alice went offline. Server sent encrypted message to Bob. To derive key, Bob requests Alice key package from server. Server return key package of Alice. Using Alice public info and own secret, Bob derive a key. This is how Alice and Bob can exchange key asynchronously. I hope you understand till this point. Let's understand this again. A and B, two users are there. Both generate secret. Both calculate public info. Using cross information, each one derive common key. Let's create group using this formula. Let's add member C. C generate secret. C calculate public info. Now, how can I add C into group? Let's replicate C. Derive key between both C. Calculate public info. Come up with common key. Let's add another member into group. Remove replicated C from group. Clear all keys that are affected. Add D into group. D generate secret. D calculate public info. Derive key between C and D. Calculate public info. Come up with common key. Calculate public info of common key, which is not immediately required. Here you can see common key 2 that will be used by all members to encrypt and decrypt message. So what is this structure look like? This is called asynchronous red jet tree. Now you can guess why it is called red jet tree. You can clearly see that child can able to derive secret of parent node. But if parent node want to derive secret of child, then there is no way. So this tree has only upward path, no downward path. Let's understand different form of this tree. This is called public state. This is common for all group member. So only one copy is maintained at server per group. This is called private state or path secret. This is very specific to each individual user. For example, user A has her own path secret. User C has his own path secret. This will not store on server, this will be stored at the client side. Now, someone might have questioned that why do we need to store path secret of tree? We can calculate all these values whenever we need. The answer is storing path secret of user will reduce warm-up time of application. Otherwise, consider that group has more than 200 members and user starting from fresh to calculate entire tree each time. Then it will take some time to calculate entire tree. That is why MLS recommend to cache path secret to reduce warm-up time. Let's pick our next problem statement. Post-compromise secrecy. In this problem, we have seen that if we remove any user from group, then how do we protect group key? So, I am leaving this problem to you to apply your own thoughts and think how can we solve this issue using asynchronous ratchet tree. Let's move to our next problem. Key exchange traffic. In this problem, we have seen that if any member get removed from group, then everyone has to re-exchange key and that will generate n into n-1 traffic to server. So, what happened in case of asynchronous ratchet tree? Just for hint, it will generate traffic of n. Now, how asynchronous ratchet tree will help to reduce traffic to n, that I am leaving to you. So here is the conclusion of entire session. MLS has solved 5 major problems: end-to-end encryption, forward secrecy, asynchronous handshake, post-compromise secrecy, key exchange traffic for add and remove of members. There are many more things for you to explore in IETF draft of MLS, like why MLS is called double ratchet, how MLS derive a new key for every single message, how double ratchet increase forward secrecy, what is welcome, proposal, commit messages. And with this all information, we have finished the messaging layer security, basics and fundamentals. Thank you for watching this video. Have a nice day.